All right, so we're going to find antiderivatives involving particular values and initial conditions. Sounds really fancy. My goal there sounds even fancier. Learn about particular solutions to differential equations, because there are two types of solutions. There's general solutions and particular solutions. So what's the difference? The general solution has a plus c in it. A particular solution, we figure out what the c is. All right, so if you know how to find an antiderivative, then this is not going to be any trouble for you whatsoever. All right, so we're given this antiderivative equation, f of x, capital F of x is equal to the antiderivative of this. So it's not given in differential form the way you might see it up here, because that's already been fleshed out for you. Under ordinary circumstances, you'd have to figure that out first. You'd be given dy dx equals this, you put it in differential form, and then set up your integral like you did on page 2. But just to kind of cut that fluff out, we're gonna cut to the chase a little bit. All right, so then the question would be, what is the antiderivative of 3x squared minus 1? And we know that we could just take the antiderivative of each part separately. What's the antiderivative of 3x squared?
X cubed plus c.
X cubed plus c, but we'll hold off on the x cubed because we're still going to account for the negative 1. Antiderivative of negative 1 is? Negative x. And so we'd have a combined plus c. We'd have a plus c for the x cubed, and we'd have a plus c for the negative x. Put it all together, it's really just one constant. All right. So that's all stuff from page 1 and 2. The new aspect of this is now that they give us a condition. They give us that f of 2 is equal to 4. It's not technically an initial condition because it's not f of 0, but it's a condition. All right. So it's telling us that if I replace all the x's with 2's, the whole result should be equal to 4. All right, so then these two would combine to give me 6. So 6 plus c would be equal to 4. And we would get the c value equal to negative 2. We wouldn't just leave it at that because I need to state my particular solution, which would be f of x equals x cubed minus x. Instead of the plus c, I would say minus 2. All right, so based off of that condition, we know that the function whose derivative is 3x squared minus 1 would be this. Right? If I take the derivative of this, I would get that. So then the question would be, well, how would I check this to make sure it works? Well, at first glance, it doesn't seem like there's any reasonable way to check it, because if I got c equals 18 or c equals negative 37, it would still differentiate to give me 3x squared minus 1. But the thing is, this should satisfy this relationship. So if I plug a 2 in, so if I were to graph this, for example, and look at the table, the x value of 2 should correspond to a y value of 4. All right? So it's really as simple as that. So use your calculator to your advantage, and life becomes a whole lot easier. All right. So the second one is along the same lines. So I won't bore you with that. I won't currently bore you with that. I'll bore you with it at some other time. But I wanted to take you through a word problem that involves these concepts. You can find on the next page. All right, so this type of problem is pretty cool, I think, because the position function for projectile motion actually comes from the concept of an antiderivative. I could show you where that comes from in a little while, but we don't actually need position functions. We never actually did, as long as you understand the concept of an antiderivative. So it's telling us the ball is thrown upward with an initial velocity of 64, initial height of 80, and acceleration due to gravity is what it almost always is, 32. We can figure out pre-calc style a whole lot of stuff if we know the position function, but we don't technically know it, right? So, and maybe even if you did know it at some point, maybe you don't remember it, and that's fine too, because we don't need it. All right, so what we're gonna do is we're gonna start off with a fact. And that fact is that acceleration due to gravity is 32. Now, it is specifically a negative 32 because it's in a downward direction. All right? That's the only source of any kind of trick question related to this topic, because direction is an important component. Velocity can be positive or negative. Forwards or up, positive. Downwards or backwards would be negative. Same idea for acceleration. Any kind of movement could have a positive or negative one. Doesn't have to say negative in the problem, right? So here it says the ball is thrown upward. So I can assume that that velocity is a positive 64, right? So things that you need to keep in mind, because you'll get, if you're not careful, you'll get the wrong sign here, and that could skew things a little bit. All right, so the hierarchy. I was impressed, honestly. It would have been cool, because then, like, not too many people opt to stay. Like, if she stayed, like, the whole way.
She was doing the math.
That's awesome.
She's doing the math in ninth period, too, yesterday. She asked to see my rules in class.
That's some serious business. That's what we call motivation. I like it.
And Junior, who's taking pre-calc.
A little preview of what's to come. Good stuff. So anyway, we have position function as our end game here. This is our goal here. Now, position, just going back in time, we talked about this a couple of units ago. Position, we would say, is normally S of t. S for position, of course. Velocity would be the derivative of your position. All right, we denote that with a v of t, but it's still the derivative of position, so it's important information. Acceleration is the second derivative of position or the first derivative of velocity. In this case, we're really just focused on the S notation, all right? Because acceleration is S double prime. That's equal to negative 32. All right. I'm going to go a little notation heavy here, just so you get a good feel for it. You won't always have to include this notation. There's some steps that you can skip, but just so you understand why things are working the way they do, it's kind of important. All right. So what this is the second derivative with respect to time equal to negative 32. All right, in differential form, because that's a differential equation, it would be d2s equals negative 32 dt squared. All right, now we can make a little bit of a conversion here just to kind of simplify things. So this notation gets out of hand very quickly. But if I tell you, and this is where it should start to kind of make sense, or at least get clarified, is that if I tell you that the second derivative of position is the same as the first derivative of velocity, then this would transform into dv equals negative 32 dt. These are the same thing. All right, they're equivalent. All right, so notation-wise, they amount to the same thing. All right, it's my way of saying don't get bogged down too much with the notation. As long as you know the hierarchy, everything works out. But it's all going to really just kind of lead to the next step where I go to take the antiderivative. All right, so that's really where the big recognition is going to come into play, because the antiderivative of dv is going to be v. And that would be equal to negative 32 dt. All right, so if you really think about what happened here, and that's the important thing, to actually think about what's going on. All we did was we took the antiderivative of whatever acceleration was equal to. Right? We just slapped a dt on it. All right? How do we know t instead of x? As a function of time. All right? So that's your indicator there. So I included all this notation so that you'd have some experience with it, but in reality, black to black. A equals negative 32t. Next step could be v equals the antiderivative of negative 32 dt. All right, so you can kind of hop over all this stuff here, but I wanted you to see what it would look like in rigorous form. All right. Now, I know I went over this, but just to address the integral of dv again, remember there's an assumed 1 again. So the antiderivative of 1 would be, under normal circumstances, it would be x, but because our variable here is v, it becomes v. Now, it's all going to have a plus c involved, so we save that for the last step. For now, we're just going to leave it c-less. All right, so velocity would be equal to the antiderivative of negative 32, which is what? Negative 32t. Now we can include the plus c. All right. Now this is a function of time. So I'm going to go back to a little bit of notation here and say that it's v of t is equal to negative 32t plus c. All right. So we can take second derivatives. We've done that before. You know, derivative of a derivative. It's just take a derivative, take the derivative again. Antiderivative is very close in terms of the process, but there's something that has to happen before you can take a second antiderivative. You've got to figure out what c is. Otherwise, you're going to have c embedded as an integral, and then you're going to create a brand new c when you integrate again. All right. So after every integration or anti-differentiation, you need to figure out what the c is. All right, so there's always going to be some information. If it's an initial condition question, there's always going to be some information that will allow you to do that. The ball is thrown upward with an initial velocity of 64. All right, so if that's the case, it's telling us that when time t equals 0, the velocity is 64. That one you can figure out in your head, but I'll show the work. Replace the t with 0. Instead of equal to 64. Left-hand side simplifies down to just a c, so c equals 64. All right, so my v of t function, I'll just write v, would be negative 32t plus 64. All right, so I'm a little iffy on my physics formulas because I always did it using calculus. So it seems like it's probably overkill, but I basically invent formulas every single time I need to do physics just using calculus. But I vaguely remember there being a formula involving like a VF and a VI. Mm-hmm. How does that go?
VF equals VI plus AT.
VF equals VI plus AT, right? That's your physics formula.
There's also that one. VF equals VF squared equals like VI plus some other stuff.
That.
Where's my blue sheet?
That might have. We'll get Panzer down here for a class visit.
2 for delta x.
In school field trip to Panzer. Does everybody walk in and say, wow? So, we have a velocity function. I now need a position function. So position is the antiderivative of velocity. So S would be the antiderivative of whatever my v function is. So I'm cutting out some of the notation because, again, it's just going to amount to the same thing. S would be the antiderivative of negative 32t plus 64 dt. And what is the antiderivative of negative 32t plus 64? Plus c. All right, they give us another condition. If you're doing two antiderivatives, you're going to need two conditions. Here it's that the initial height is equal to 80. So that's telling us that S of 0 is equal to 80. So S of 0, I'll show the work, negative 16, 0 squared. When you do this on your own, you won't, in a lot of cases, have to show the work. But in some cases, they don't clean up as simply as these do. 80. But in this case, when you plug in the 0, everything cancels out except for the c, which is nice. All right, so we end up with S of t would be negative 16 t squared plus...
It's over, but it's never over.
It never is. And considering there's a part B.
Oh my god.
Nah, the part B is easy.
Yeah, can we use our blue sheet?
Nah. Under normal circumstances, I'd say why not, but if you use those formulas, then you're not doing the calculus, and you need to do some calculus. Now, if you want to get creative. So anyway, we get this function here. Now, if you remember the position function from pre-calc, or whatever the physics variation of it is, 1/2 at squared plus VO t plus SO. All right. If gravity is negative 32, 1/2 negative 32 give you negative 16. Initial velocity was 64 in the upward direction. Initial height was 80 in the upward direction. All right. So we just basically invented the position function just by knowing gravity and how to take an antiderivative. If you do that with general terms, meaning instead of actually putting in negative 32, if you actually just leave it as A, you would get this formula. It's a pretty cool realization that it's totally within your capability at this point to invent formulas that people in physics class have to memorize. That's pretty solid stuff. Now, when does it hit the ground? That's not bad. Because now that I have a model to represent its path, it would be when the height of that object is equal to 0. So negative 16 t squared plus 64 t plus 80. Whenever people start factoring out GCFs and stuff like that, I'm like, that's cool. It's like this magical approach, like just factor and everything. I keep thinking back to Ebony Maw from Infinity War, when he's like, "Oh, how quaint! You must be popular with the school children." You know, like when people are doing that, I was like, "Yeah, I'm just gonna use my quadratic formula program."
Where was this in?
Algebra need not concern you at this point. It's not an algebra course. Every now and then you have to show some work to do the derivative stuff. But here, just basic equation solving stuff. Now, when does the ball hit the ground? well, it implies, I think, a future event. So 5 seconds later.
I feel enlightened.
All right. As you know, there's a time and a place for negative values of time, but the ball is being thrown upward from a height of 80. That negative time would be at a height of 0, but it would have to be before it was 80 feet in the air. But if the ball was held immobile, then it wouldn't be parabolic. So some other function would represent that ball's movement. So it's irrelevant, basically. So 5 seconds after the ball is thrown is when it would hit the ground. Easy. What are we talking there? Like 8, like 10 stories up? Whoever threw this put some stank on it. Because it's not, I mean, 5 seconds is a pretty serious amount of time in the air. Even from 80 feet up. So, but now that you have a function model, you can determine what its maximum height was, so you can really see just how much oomph was involved. All right. So that's a nice little application of this concept of an antiderivative. There's definitely a lot more applications of it. In college, we fill an entire course and a half with really just investigation of derivatives and antiderivatives. So it's like the first course and a half is where you just learn how to do it all. And then after that, it's like you learn why you spent a course and a half doing it all. You know, so now we're kind of bridging into the why part as opposed to just the how, right? And that's why, you know, groupings are going to be important because, you know, if you have good sounding boards, you can come up with some really good ideas related to this. All right, so end of speech.